Okay, so yesterday we were talking about inference methods and regression. So our two forms of inference that we'll talk about in this level of statistics are confidence intervals and hypothesis tests. The first one we're going to talk about for regression is hypothesis tests. So if you remember from yesterday, we started with our null, and our null, when we're dealing with scatter plots, we're dealing with two variables, a response variable and an explanatory variable. So my null is that there's no linear relationship between those two variables, because that wouldn't be very interesting. So B1 would be 0, meaning it would have a slope of 0. And all that's saying is no linear relationship between, between A and B, between X and Y. Okay, well, the alternative is that there is some kind of relationship. So alternative hypothesis is going to be that your slope is either greater than 0, so that would be a positive association. That would be examples like as your waist size increases, your body fat increases, so there would be a positive slope. B1 would be greater than 0. Or maybe B1 is less than 0, so negative slope. That might be something like draft pick and the amount of salary you start with. So for example, if you're the first draft pick, you're going to be making more than the second draft pick, and you're going to be making more than the second draft pick will be making more than the third draft pick, and so on and so forth. So that would be a negative linear relationship. Or maybe we're not really sure which direction it is, but we're just trying to test if there is something. So just not equal to. And so all three of those things are just saying that there is a linear relationship between X and Y. Again, your explanatory variable, your response variable. Okay. The conditions for linear regression hypothesis tests will be a little bit different than well, there will be some similarities, but there's going to be a few more conditions that we haven't seen yet. So the first is that the data has to be approximately straight to start with. So that's your scatter plot. Okay, so the scatter plot needs to be approximately linear, and all that's saying is that we're looking at roughly linear dots. Okay, if the dots are not roughly linear, that's going to be when we consider re-expression. That was chapter 9. Okay. So re-expression, that would be if I'm going to take the log of all of those X values, or I'm going to take the square root of all of the Y values. And we talked about the ladder of powers. That's from chapter 9. We'll try to do an example of that, but most often if we've re-expressed the data, we're just being given the computer output, and you are not actually responsible for the re-expression. On the free response on the AP test, I have yet to see a single problem where they ask you to do the re-expression, but you will be expected to understand the computer output for that. So we'll see some examples of the computer output. Okay, our second condition is independence. So the individuals in the study are independent of each other. Okay, well, that's kind of hard to confirm. If we go back to the waist by body fat percentage scatter plot, we don't really know how those individuals were, we don't know who those dots are or where those data points came from. So it's kind of hard to check condition 2. And the way we check condition 2 is kind of by checking condition 3. So if the data was obtained randomly, if the individuals were obtained randomly, either through a simple random sample or just random sample or some other randomized selection process, then we can make the assumption that they are independent of each other. Okay, so individuals were randomly selected, or assume the sample is representative of the population. Make that a little smaller. Okay, this is for if you went out and you just observed. So let's say, for example, the body fat or the MLB baseball salaries. Well, all I did was I went out and I looked at those people. I obtained a sample. If I've done an experiment, so for example, if I looked at so that will only be the case if we remember back from the last 2 units. If we're looking at sample versus experiment, we are only looking at samples for these lines of regression. So the only way to satisfy condition 3 is a random selection. If it doesn't state that they were randomly selected, we just have to assume the sample is representative. You won't see experiments. So if we don't have this, if we don't have a random selection, and you don't feel comfortable assuming that the sample is representative, they've given you reason to think you can't make that assumption, there's one other way. We can look at the residuals. The residuals can be random. If the residuals are random, then we can feel comfortable stating that the individuals were randomly selected. So what I'm actually going to do is I'm going to kind of insist that you use one of these two. So you can scribble out that last one. We really kind of don't want to make that assumption if we don't have to, and so it's either going to state that they're randomly selected or you're going to have to look at the residuals. Remember, residuals are how much I'm off by. So that's how much was I above the line of regression, how much was I below the line of regression, etc. Okay, equal variance. Equal variance is the idea of spread. So if we remember spread, if we think back to our standard deviation of residuals, so S sub E, our spread needs to be consistent. So both of these graphs that we see here would be fine. This one is consistent. They're all consistently close to whatever imaginary line I would draw through here. Let me draw one. Let's say that's our line of regression. They're all consistently close. So it's equal variance, equal spread. Let's start this one right about here. Okay, so they're again not as close, but it's approximately equal. So they're all roughly spread out from the line. So an example of what we wouldn't want, let's shrink this down just a little bit. So an example of what we wouldn't want, let's say we're looking at a graph like this. Where the dots all start out seemingly close together, but then maybe they start to fan. So if I were to draw a line through all of these points, we'll see that I would still call this approximately linear, but as I draw a line through these points, is there one section where the spread is not equal to another section? So if we look down over here, we'll see the spread, the standard deviation of residuals, or the variance of those residuals, is fairly small, and over here it's fairly big. So this would be bad. This would be not equal variance, or not equal spread. Okay, so if we jump back to those conditions, you can even change this if you'd like. This is variance or spread. So we need to know, we need to make sure that the spread around the line of regression is approximately consistent. Okay? If you can't be sure of this, the other thing we can do is we can look at the residual plot. So if we've got random residuals, we're fine here. We can say that. So let's come back to this page. Over here, if I was looking at residual plots, let's talk a little bit about residual plots. Okay, so residual plots are, again, the x values by the residuals, so the amount that I'm off by. Okay, so residual plots. We've got our x values are our x-axis, same as up here. And now our residuals are what we're looking at to see if there's a pattern. So here, we'll see that all of the residuals are fairly small. So let's put all of these on the same axis. Let's call this 1, 2, 3. We'll call this 1, 2, 3, and we'll make these negative. Okay, so what each of these dots on the residual plot are going to represent are each of the x values and how much I was off by. So how much I was over the line, how much I was under the line. Looking at this first one with a very small spread, we're going to see that most of these residuals, the amount that I was off by, are pretty small. And I'm just kind of eyeballing this for explanatory purposes. But we'll see no real pattern here. Some above, some below, but we still are kind of visually able to tell that the spread is small and it's constant. Okay, over here for this second graph, so this middle one, well, we've got some bigger residuals. So there were some dots that were, like for this one, or for this one, that were much farther away. So they've got bigger residuals. And we had some that were well above the line of regression and some that were well below it. So looking at that residual plot, do we see a pattern? No. So the residuals are random, which means that this spread was approximately consistent. Over here, if we were looking at this one that we already know is bad, this graph, probably don't want to work with because the spread is not consistent. So over here, what this residual plot would look like would be that the residuals started out for lower values of x as producing very small residuals, and then there was a range of x values where the residuals got larger. So we see that fanning, and that fanning tells us this graph is no good. So the residual plot, just like the original data plot, tells us we probably shouldn't move forward with an inference test. Okay, so that's what this little comment is about. So we can either just look at the spread, or we can see if the residual plot is random. And finally, the last condition, normal. What we want are normal residuals. And so if we think back to, and careful, that's not the residual plot. What I mean is approximately normally distributed data in the original data. So if we come back to our very first example, right up here. So with this example, when I was looking at people with a 38-inch waist, okay, I had a lot right here at the center, and then I had a few, and then a few more out here. Okay, so I want the majority to hang out around the center, and then a few above and a few further below. Okay, that can be done by making a histogram for every single value here. All those possible x values. But if we remember, we run into the problem of this is continuous data. I don't want to make a histogram for all of those values. That's going to be time consuming and just not really feasible. So that's kind of the idea here. I want those individual residuals, so the dots around the line, to be approximately normal, because that line needs to go through the center of all of those distributions. So if we're looking down here now, the line should go through the center of all those distributions, and all those distributions of people with 30-inch waists and people with 35-inch waists and people with 40-inch waists and people with 45-inch waists. I'm hoping that those people, I've got some that are above, most right around the line, and then some right below. That's what that last condition is saying, and that's what the picture in the last condition is referring to. Right down here. So what I'll put here is let's see. So that explanation, how do we summarize that into a single sentence? Let's say that the histogram of the residuals is unimodal and roughly symmetric for all x values. That was the bell. So we're just saying that the histogram of the residuals is unimodal and roughly symmetric for all x values. Really, we just kind of want again, the spread to be consistent. So all you'll say here is that we have some over predictions, some under predictions, and you guys will either see that in that image will be provided, or there will be another way that we kind of satisfy this condition. We'll see examples of that, of how you actually phrase this fifth condition. So we've got 5 conditions. That's a lot to keep track of. 2 and 3 kind of go hand in hand. The way we satisfy condition 2 is kind of by satisfying condition 3, by showing that there was random selection or random residuals, and that helps us assume that the individuals are independent of each other. Your acronym for the conditions, you may be able to just figure it out by looking down the bottom of this, is SIREN. So if you have to come up with an acronym for that, SIREN is what we're going with. I'll talk more about conditions. I know you guys have about 40 of these floating around in your heads. So we'll discuss kind of next week how you work with all of those different conditions on the actual free response problems. But just know that these are the ones that we'll need to move forward with a hypothesis test for regression. All right, so our plan. The conditions are met, so the sampling distribution follows the sampling distribution of sample slopes. So from yesterday, what this means is the sampling distribution of sample slopes. Let me change the color. All of these sample slopes follow a t distribution. Okay, that t distribution will be centered at beta 1. Okay, so the t table and t stars and all of those fun values will be coming back into play. And all you're going to state for the plan, the type of test we're going to run, is you're going to tell the reader that you're doing a linear regression t-test. And that is exactly what it is called in your calculator. So if we pull up the calculator, let's go to stat, tests, and let's just go up. Almost there at the bottom, linreg t-test. All right, or you can just call this a linear regression t-test. If you're nervous, you'll miss points, or if you're just not feeling lazy. But both, as far as the rubrics I've seen go, are fine. Okay, I'm going to go ahead and stop the video here just because they're easier to upload when they're a little bit smaller. And I will continue with part 2 in just a moment.